Hello, my name is Siavash Rezazadeh, and I'm the Director of Robotics, Locomotion, and Control Lab at University of Denver. Today, I want to talk to you about how using backdrivable and quasi-direct drive actuators can help us design and control better robots for human-like locomotion. So to give you a little background, most of common actuators of the robots consist of an electric motor in series with a gearbox for speed reduction and torque increase. So this is the system that we are talking about, a motor in series with a gearbox. But elimination of gearbox, i.e. having a direct drive actuator, just the motor, can help in several characteristics of actuation. That includes, it simplifies the maintenance because you don't have the rather complicated and high maintenance parts of gearbox anymore. It decreases the friction. You don't have the energy loss in the gearbox. It increases the stiffness because again, you don't have the compliance in the gears. It can eliminate the backlash, which is usually an inherent characteristics of gearboxes, and it can reduce the reflected inertia of the gearbox, which is typically proportional to the square of the gear ratio. So most of these benefits can be lumped into under the category of passive impedance of the actuator. So the reflected inertia, damping, friction, stiffness, all of them can be lumped into passive impedance that is increased as a result of having a gear ratio. Now, if the passive impedance of the actuator is zero, means that you don't have gearbox, then you can control the torque at the joint level using the current control of the motor driver, which usually works very well. So that simplifies the torque control of the joints to a great extent because you won't have torque sensors and the complexities associated with that, increased cost, increased weight, and the fact that torque sensors usually don't work well in low torques, less than 10% of their full scale. So this is a very neat idea, but it's pretty old. It first proposed in early 80s by Rezazadeh in the CMU direct drive arms that he developed at Carnegie Mellon. So some 20 or 30 years later, this idea, which Rezazadeh applied to manipulators, was used in hexapods like Rex, and then quadrupeds like MIT Cheetah, Ghost, and Stanford Drogo. The idea was that these direct drive actuators could negotiate rough terrains better and could manage impacts better because they don't have gearbox and they can do good force control. So all these hexapod and quadrupeds showed impressive performances, and the direct drive actuators, or quasi-direct drive, meaning having low gear ratio, but not gear ratio 1-to-1, played a great role in their success. But let's talk about bipeds now, which is the main topic of this talk. So the first time that I noticed the importance of backdrivability in a biped was back in 2015 when I was working on control for ATRIES for the ARPA Robotics Challenge. With ATRIES, as you see, we accomplished a good performance, very dynamic walking with high speed. And back then it was, I think, the highest speed that any biped in 3D achieved. And still, excluding the new Atlas, still it's one of the fastest robots that have worked in 3D. So to give you a little background about the idea of design and control of Actuators, Actuators was designed to embody the dynamics of the spring mass model, in that it had two springs, as you see in the middle figure, that when worked together, they could simulate a spring in the leg length direction. It had very light legs with negligible mass, and the springs which were in series with the motors at the hip. So theoretically, if the motors were held stationary, the springs should be able to do all the deflection of the leg and walk like a spring mass system. But in practice, what happened was that we had to provide almost half of the compliance of the leg using the actuators. So the springs that we could use for Actuators resulted at the beginning when the motors were held stationary to a pretty stiff gait. And after every impact, the robot kind of jumped back into the air. We tried to decrease the stiffness of the springs to have a more compliant gait, but the physical constraints of the system, the large deflection of the springs, prevented us from that. So what we did was just reduce the position control gains of the motors, so that the motor could also backdrive under the stance load. And it worked, as you saw in the previous video, pretty well. In this video, this strategy is a little more visible, wherein Actuators is walking over an unexpected obstacle during a step down and a step up and a step down. And as you see in a step down, the leg deflects to a large extent in order to absorb the extra energy and stabilize the motion. So this reflex-based control, which I designed for a step up and a step down, was also based on backdrivability of the motors under the high load that a step down causes. So the fact that the motor to some extent can do the job that we expect from the spring begs the question that, can we remove the spring from the leg and give all the work to the motors? Meaning, use the compliance of the motor, design the control so that the compliance of the motor backdrives the actuators and they can act like a spring. To study this, when I joined Bobby Gregg's lab at UT Dallas, I did a study of a simulation study of an anthropomorphic leg. So here, unlike Actuators, the leg segments have non-negligible mass, and we have feet and ankle actuation. And I adapted the control of Actuators to this system by dividing the leg length actuation between knee and ankle actuators. So it starts from a stationary, rather large disturbance force pushes it backwards, and then it stabilizes itself to the desired velocity of 1 meter per second. So in this next plot, what happens is a little more clear. So the system starts from the stationary state, 0 velocity. The force makes the robot go back to negative velocity. And once the force is removed, the robot stabilizes itself to the desired velocity of 1 meter per second. So why this result is important? Specifically because we are working on a development of a prosthetic leg. So in prosthetic legs, unlike robots, we are very much constrained by the mass of the system and also the sizing of the parts of the prosthesis. So if you can remove the springs, it simplifies the design. It reduces the size, which is important again for self-contained prosthesis. And it can reduce the weight because we can get rid of extra parts. So this is the UTD leg 2, which was designed mainly by Tove Ellery and Chris Nestler. And in which we developed a quasi-direct-drive actuator for knee and ankle joints, and then control them by impedance control. The gearbox of this system was a special type of planetary gearbox, since the traditional planetary is constrained by low gear ratio, typically less than 10:1. We use this extended type of planetary, which is called the step planet compound planetary gear transmission, SPC-PGT. And the gear ratio, both for ankle and knee, was 22:1. So this type of gearbox has the benefit of having larger gear ratios with the efficiency pretty much the same as traditional planetary, because the number of the machine gears is almost the same. Unlike the two-stage planetary, which reduces the efficiency by a great extent. So this quasi-direct drive led to a lot of benefits, including this knee free swing. As you see, the motor is off here. And when I release the leg, it just freely swings by itself. And it matches the characteristics that we see in human walking, wherein humans use gravity to swing their shank forward when they are walking. So getting the energy from gravity, we can regenerate it back to batteries and improve the efficiency of the system. Another benefit of this, this design, as was originally proposed by Rezazadeh, is open loop impedance control. So because the passive impedance of the actuator is pretty small, we can do a simple PD controller on the joint level and achieve a good impedance control. So in this experiment, I'm moving the actuator with the lever arm. The lever arm is attached to the actuator through a force sensor, 6-axis load cell. So we can measure the load that I'm applying and the position that the actuator is moving. So if we compare the desired from the impedance control equation and the load that the load cell is reading, you can see they match pretty well. So based on this, we can we can control the joints of the prosthetic leg to match the stiffness values that we know for human walking with open loop impedance control, with this simple PD control that acts like an impedance control. So this is significant because it can avoid the long tuning sessions that non-backdrivable actuators are accompanied with. So in Michael Goldfarb's group's work on their powered prosthesis, which was non-backdrivable, it was reported that they started from human normative impedances, but after tuning, the values that they found was pretty different, and the tuning session was pretty long. So this is a benefit of backdrivable actuator that eliminates this tuning session or shortens them significantly. So we tried this control, this open loop impedance control, with an amputee subject. And as you see, the amputee subject can walk in with different speeds pretty well. Note that the tuning was minimal. We just used the normative human impedances for different speeds, and the subject can walk with just a few minutes of acclimation phase. And probably because of this short acclimation, you can see that the subject swings the leg forward the way that they do usually with passive legs. And in this plot from the energies that we calculated and read from the outside the battery, you can see that the regeneration that we talked about earlier during the free knee swing actually happens here at almost 75% of the gait cycle. So the green curve shows the power of the knee, which is negative at that point. And the blue curve shows the electrical power of the battery, which is also negative, meaning the power is going back to the battery. And this regeneration definitely will help the efficiency of the system. So with this motivational examples, we get to the problem of how to design backdrivable actuator for human-like walking. So in a very interesting work by Sang-Bae Kim's group, by Pat Wensing and others, they showed that if we increase the gap radius of the motors and decrease the gear ratio, because the motor has higher torque now, the torque density of the actuator increases. But at the same time, they showed that the reflected inertia doesn't change, and the maximum acceleration ability, which is defined as the maximum torque divided by the reflected inertia, will decrease. In addition to that, the maximum velocity of the actuator at the joint level also will decrease if you use a larger motor with lower gear ratio. And this is important because oftentimes you are limited by voltage. The number of cells of the battery can be limited. The voltage of your motor driver can be limited, or you are limited by the safety concerns. Usually in the systems that work with humans, you should have a voltage less than 48 volts. So all these factors show that we have an optimization problem in hand with objectives and constraints that we talked about and also will talk about shortly. Another constraint that is, again, oftentimes is neglected is the linear characteristics of the DC motor. So DC motor the operational range of DC motor is like the diamond shape that is shown here. So to be feasible for the motor, the operation point of the motor should be inside the diamond. So if you have that red point that's shown there, you see that its speed is less than maximum speed, its torque is less than maximum torque, and probably even less than continuous torque. And still this point is infeasible. So it's not enough to check only maximum velocity and maximum torque. We need to check all the points of operations and compare it to this diamond shape operational range. So once we define our constraints, we need to talk about our objectives for this design problem, this optimization. The first objective is efficiency, the most natural objective in design of legged robots. And it can be formulated as I shown here by this integral during a gauge cycle, which is essentially the power loss due to damping and the winding loss of the motor. And then another objective we can have is the quality of the control performance. But how we can formulate the control performance? This is the work that was done by my students at University of Denver, Chatru and Drake. And they proposed that we use two different metrics for stance and swing phase controls, because fundamentally they seek two different goals, and it makes sense to have two different objectives for them. So for the stance phase, they proposed that we use the passive impedance that we talked about earlier as our performance metric. So because in the stance phase, we are interacting with ground and force control is, or impedance control is of prime importance, it's vital to have low passive impedance so that the actuator can do good force control. Next, in swing phase, the control characteristics is shown by how fast you can step forward or backward, depending on the disturbance force that is applied to the system. And this idea is actually comes from the work of Martin Wiese. And this is a very interesting sentence that he has used in one of his papers. And it says, you will never fall forward if you put your swing leg fast enough and far enough in front of your stance leg. Okay, so whatever disturbance is applied to you by taking a fast step, you can always stabilize yourself. So this would be the characterization of our swing phase control quality. Once we have the objectives, then we can talk about optimization parameters and model of the system. So to have an anthropomorphic leg, you can see here we have thigh, shank, and foot. And the hip actuator is at the hip. The knee actuator is somewhere up the thigh and connected to the shank through a forward linkage. And similarly, the ankle actuator is somewhere up the shank and using a forward linkage actuates the foot. What is interesting here is that the mass of the actuators affect the performance of the previous actuators. So if you increase the mass of the ankle actuator, the swinging of the swing characteristics of the knee and hip will be affected. If it's heavier, if the ankle actuator heavier, swinging will be more difficult. And also, it will affect the passive impedance of the actuator because it affects the way that you can do force control. Also, we have gearbox systems here. We consider both single stage and extended planetaries with all the geometric characteristics and strengths of the gear teeth and so on. So this is a rather complicated model that we use for optimization, and we try to consider as many parameters as possible. So with this, the optimization can be formulated like this with 3 sets of optimization parameters. MH, MK, and MA are the motors that we are selecting. Assume that we have a set of motors that we want to pick among them for our actuators. GH, GK, GA are the design of the gearbox, the diameter of the gear wheels, the modules, the number of planets, even the material if you are interested, and so on. And LK and LA are the design of the 4-bar linkages. And then the objectives, as we talked about, are efficiency, passive impedance, and step time. And the constraints, again, we talked about earlier. These 4 constraints determine the feasibility of the design. So this is a multi-objective optimization with 3 objectives. So this is an example of solution for this multi-objective problem. The figure shows the Pareto front we found for a design problem. And as you see, each point of the Pareto front shows 30 design parameters that we just talked about. And we use this design optimization for design of our new biped Mithra, which has been just assembled and is undergoing initial testing. It's designed to have characteristics of an average human, height of 175 centimeter, weight of almost 71 kilograms. The actuators are very backdrivable because we have optimized the passive impedance as one of our objectives. In the mechanical design, we tried to have a mass distribution and length comparable to those of humans, so that it can serve as a platform for testing human-like walking. And in terms of strengths and also actuator ability, it should be able to achieve a running of 3 meters per second. So hopefully it can go under, it can undergo the initial test soon, and we can start testing locomotion with it. And this is an example of our initial tests. Again, the free swing, the knee can easily be back driven, and when we release it, it just swings freely forward. Thank you very much for your attention.